Hello AP Chemers, we are talking about thermodynamics, and we had said that there are two driving forces in nature that determine whether a reaction is going to be spontaneous or not. Those are entropy, delta S, and enthalpy, delta H. And so if it's favored by both, the reaction will be spontaneous at any conditions. If it's not favored by either, then the reaction is not going to be spontaneous. It's not going to occur naturally under any conditions. But if it's favored by one and not the other, then we have to look at the conditions. So that means at some temperatures it will be, and at some other temperatures it will not. And so to figure that out, we looked at delta G. Delta G is Gibbs free energy, and it's a made-up variable that combines delta H and delta S together. And we saw that if delta G is negative, then the reaction is spontaneous. At those conditions, if delta G is positive, then it is not spontaneous. And so we're going to look at a couple of methods for how to calculate delta G. So the first method that we're going to look at, similar to delta H and delta S, delta of anything is final minus initial, so products minus reactants. And so we can say delta G for a process is the sum of the Gibbs free energy for the products minus the sum of the Gibbs free energy for the reactants. So you have a table of thermodynamic variables here. And so we've looked at delta H of formation before. We've looked at delta S, or the entropy of formation of different substances, this chapter. And so now we're going to look at delta G of formation, the Gibbs free energy of formation. It is measured in kilojoules per mole, just like delta H. And just like delta H, delta G for an element in its natural state is equal to 0. So you'll see like aluminum solid is 0, beryllium solid is 0, carbon as graphite is 0. You'll see that fluorine as F2 gas is 0, and so on. So the Gibbs free energy and the heat of formation of an element in its natural state are both zeros, but the entropy is not 0. So that's something to keep in mind. So we can use these values in order to calculate delta G for a reaction. So let's say we want to burn some propane, and we want to calculate the Gibbs free energy for this reaction. You'll notice that those variables have like a little degree sign next to them. That means that they're at standard conditions. So that's 1 molar solutions, 1 atm of pressure, and 25 Celsius. And so this will only calculate delta G at standard conditions because we're using the values at standard conditions. So that's not going to help you calculate delta G, at 100 Celsius, for example. It's only going to help you if you're at 25 Celsius. So what we're going to do is we're going to say delta G for the reaction is equal to the products minus the reactants. And so I'm going to start our products here. We have 3 moles of CO2. And let me find my table. So the value for CO2 is negative 394.359 kilojoules per mole. And we have 4 moles of H2O. Value for that one is negative 228.52 kilojoules per mole. So those are my products. I'm going to subtract my reactants from that. And so I have 1 mole of C3H8. The value for that one from the table is negative 23.49 kilojoules per mole. And then I have 5 moles of O2. But because this is an element in its natural state, the value of it is 0 kilojoules per mole. So products minus reactants all together, I get that delta G for the reaction at standard conditions is equal to negative 2,074 kilojoules per mole. And so that's my answer. And because it's negative, that tells me that it is spontaneous. So again, this only works if you are at standard conditions. reactions. The next method is the method we used in the last lesson, which is delta G is equal to delta H minus T delta S. And this will work for any temperature. So either you're going to be given delta H values and delta S values, or you can look up the values in our tables from our tables here, the delta H and the delta S. So you could do for delta H products minus reactants, for delta S same thing, products minus reactants, get the value for the delta S and the delta H. Now, just a little disclaimer here. So delta H and delta S and delta G from this table are all at 25 Celsius or standard conditions. Delta G changes dramatically if you change the temperature. We saw that for some reactions it could be spontaneous at one temperature and non-spontaneous at another temperature. So delta G changes a lot based on the temperature. However, delta H and delta S change very slightly based on temperature. And so we can actually use the values at standard conditions for a different temperature when it comes to delta H and delta S. We cannot do that for delta G. So if you are trying to calculate delta G at a different temperature, again, you may use the values here for delta H and delta S at different temperatures, but you have to plug it in into delta G is equal to delta H minus T delta S, and that is going to take care of the change in the temperature. We are making the assumption that the delta H and the delta S are about the same at different temperatures, and that's an okay assumption to make. We just can't do that for delta G like we said. So if I want to calculate delta G for the same reaction, but using this equation, what I will do is I'm going to calculate delta H for the reaction by doing heats of formation of the products minus heats of formation of the reactants. And so I'm going to start with my products. I have 3 moles of CO2, 393.5 kilojoules per mole, plus 4 moles of H2O, 241 kilojoules per mole. Oh, sorry. And then, so this is products minus the reactants. I have 1 mole of propane. And my value for that one negative 103.8 kilojoules per mole plus 5 moles of O2, and remember with delta H the value is 0. Okay, products minus reactants, I get delta H of this reaction to be I got negative 2,043 kilojoules for delta H. Okay, I'll do delta S, same thing, so products minus reactants. So we have 3 moles of CO2. I'm going to round to the tenths place here, 213.7. This is joules per mole Kelvin. And I have 4 moles of H2O. Value is 188.8 joules per mole Kelvin. Minus my products, I have 1 mole of C3H8. 269.9 joules per mole Kelvin. Plus, then I have 5 moles of O2. And remember, that's not 0. It is 205.1 joules per mole Kelvin again. I got delta S for my reaction to be 101 joules per mole Kelvin. And so then I'm going to calculate delta G. So either you're going to have to calculate those values by doing that, or they might be given to you in the question. But either way, once you have delta H and delta S, you could say delta G is equal to delta H minus T delta S. Delta H we got to be negative 2043 kilojoules per mole. Minus T, we're doing it at standard conditions, so 298 Kelvin. Delta S, remember this is joules per mole Kelvin, but this is kilojoules, so to add them we got to convert one or the other. I'm going to go ahead and convert this, so it's 0.101 kilojoules per mole Kelvin. And all together, when I calculate my delta G, I got negative 2,073 kilojoules. And so comparing this value with the other method, they're pretty much the same, right? Look at that. So no matter what method you use, you should always get the same value. If this was a different temperature, then you could just plug in whatever temperature and it'll give you delta G at that temperature. The third method is using the summation method, which is very similar to Hess's law. So if you're given different reactions with their delta G's and you add them up to get an overall equation, then you can add their delta G's to get the delta G for the overall equation as well. So just like Hess's law, but with delta G's as opposed to delta H's. So let's do that. So the reaction we're interested in is this reaction right here. Sulfur solid plus O2 gas yields SO2. So I'm going to try to find these in my reactions here. So sulfur solid is in this first reaction. It's the correct coefficient, correct side. So I'm just going to rewrite this. So sulfur plus 3/2 O2 yields SO3. Delta G is negative 371 kilojoules. Oxygen is next. Oxygen is in both of the reactions, and so when it's in both of the reactions, just like with Hess's law, you ignore it because it's in both of them. The next one's SO2. So SO2 is in this second equation. It is the wrong coefficient. We need to make it say 1, but this says 2, so we need to divide this equation by 2. It's also on the wrong side, so we need to flip this and divide by 2. Flip and divide by 2. So we're going to flip it, divide by 2. So it's going to be SO3 yields SO2 plus 1/2 O2. Delta G is going to be flipped, so instead of negative, it's going to be positive. And it's also going to be divided by 2, so that is 71 kilojoules. Let's check that we did it correctly. I see SO3 here, SO3 there. 3/2 O2 is the same thing as 1.5 and half O2, so the half O2 cancels with one of these to make it 2/2, which is 1 O2. So S plus O2 yields SO2. That is the equation that I was looking for, so all I do is add up my delta H's, delta G's, so negative 300 kilojoules is my answer. So those are the three methods that we can use to calculate delta G.